The search for alien life begins with the search for habitable planets. Scientists have identified several factors that make a planet habitable, including the presence of water, a stable climate, and a protective atmosphere. The discovery of exoplanets that meet these criteria has led many to believe that the chances of finding alien life are higher than previously thought. One of the most promising methods for detecting alien life is through the study of biosignatures, signs of life that can be detected from a distance. These can include the presence of oxygen or methane in a planet's atmosphere, as well as the detection of complex organic molecules. While there is still much we don't know about the conditions necessary for life to exist, scientists have identified several potential locations where extraterrestrial life could thrive. These include subsurface oceans on icy moons like Europa and Enceladus, as well as the potential for microbial life on Mars. The discovery of extremophiles, creatures that can survive in extreme environments like deep-sea hydrothermal vents or acidic lakes, has also expanded our understanding of the conditions necessary for life to exist. This had led some scientists to speculate that alien life may exist in environments that were previously thought to be inhospitable. The possibility of intelligent alien life existing in the universe has been a topic of fascination for centuries. With the vastness of the universe and the sheer number of planets that could potentially support life, it seems almost inevitable that there must be other intelligent civilizations out there. However, despite decades of searching and theorizing, we have yet to find any conclusive evidence of extraterrestrial life. One of the main reasons for this lack of evidence is the vast distances between stars and planets. Even with our most advanced telescopes and instruments, it's difficult to detect signs of life on planets that are light years away from us. The search for extraterrestrial life is complicated by the fact that we are not entirely sure what we are looking for. We assume that any intelligent civilization would use some form of communication or technology that we could detect, but there is no guarantee that this is the case. In recent years, astronomers have discovered thousands of exoplanets, many of which are located in the habitable zone around their host star. This is the region where conditions are just right for liquid water to exist on the planet's surface, which is considered a key factor in the development of life as we know it. As mentioned earlier, the promising area of exploration is the search for biosignatures. These could include the presence of certain chemicals in a planet's atmosphere, or even the detection of artificial structures or signals that suggest the presence of an intelligent civilization. Of course, the possibility of finding intelligent alien life raises many questions and challenges. How would we communicate with them? What would their culture and society be like? Would they be friendly or hostile? The Drake equation is a mathematical formula developed by astronomer Frank Drake in 1961 to estimate the number of intelligent civilizations in the Milky Way galaxy that are capable of communicating with us. The equation takes into account several parameters that are believed to be important in the development of intelligent life. In this equation, n is the number of communicative civilizations in the Milky Way galaxy, r is the rate of star formation, Fp is the fraction of stars that have planets, and E is the average number of planets per star that are capable of supporting life. Fl is the fraction of those planets where life actually emerges. Fi is the fraction of those planets where intelligent life emerges. Fc is the fraction of those civilizations that develop technology capable of interstellar communication. And L is the length of time that such civilizations continue to communicate. The Drake equation is not a precise tool for estimating the number of communicative civilizations in the Milky Way galaxy, as many of the parameters are based on assumptions and uncertainties. However, it provides a framework for thinking about the factors that may be important in the development of intelligent life and the potential for communicating with other civilizations. The Fermi paradox is a perplexing and thought-provoking concept that has puzzled everyone for decades. The paradox is named after physicist Enrico Fermi, who famously asked the question, "Where is everybody?" during a discussion about the possibility of extraterrestrial life. The Fermi paradox refers to the apparent contradiction between the high probability of the existence of extraterrestrial civilizations and the lack of evidence for their existence. According to the Drake equation, with some reasonable assumptions, there could be as many as 10,000 communicating civilizations in our galaxy alone. Yet, despite decades of searching, we have not found any conclusive evidence of extraterrestrial life. There are several possible explanations for the Fermi paradox. One theory is that intelligent civilizations may self-destruct before they are able to make contact with other civilizations. This could be due to war, environmental collapse, or technological advancement that leads to their own destruction. Another theory is that intelligent civilizations may choose not to communicate with others. They may have their own reasons for remaining hidden, such as avoiding interference or preserving their own culture and way of life. The possibility of a great filter is another explanation for the Fermi paradox. This theory suggests that there may be a significant obstacle that prevents civilizations from advancing beyond a certain point. This could be a technological or environmental challenge that proves insurmountable for most civilizations. Finally, it is possible that we simply have not searched enough or in the right places. Our current methods for detecting extraterrestrial life are limited, and it is possible that we have missed signals or signs of life that are beyond our current capabilities. Let's look closer at the so-called Great Filter. The concept of the Great Filter suggests that there may be a significant obstacle or series of obstacles that prevent civilizations from advancing to the point of interstellar communication or exploration. The idea of the Great Filter was first proposed by economist Robin Hanson in 1996, and it has since gained traction among scientists and researchers in the field of astrobiology. The theory suggests that there may be a point in civilization's development where it faces a challenge that is so difficult to overcome that it ultimately leads to its extinction. As the Drake equation indicates, there must be a large number of observable alien civilizations in the universe and in our galaxy in particular. However, the Fermi paradox shows that in the presence of all the conditions for the emergence of extraterrestrial civilizations, Earthlings do not observe any. Robin Hanson suggested that a series of evolutionary steps must be completed for an interstellar civilization to emerge. The emergence of a star system with planets on which the appearance of life is possible. The appearance on one of the planets of self-reproducing molecules, RNA for example. The emergence of simple single-celled life, such as prokaryotes. The emergence of complex single-celled life, such as eukaryotes. The emergence of sexual reproduction. The emergence of multicellular organisms, the emergence of animals with a developed brain that use tools, achieving the current state of humanity, and finally the spread of civilization through the process of space colonization. At some point in the evolution from the first to the ninth step, there is a certain barrier that is extremely unlikely or even impossible to overcome. It can be expressed in a combination of natural factors that don't allow life to arise and develop sufficiently, or in the death of intelligent life as a result of their own actions or the activities of other civilizations. According to the Great Filter hypothesis, at least one of these moves, if the list is complete, should be unlikely. If this is not an early step occurring in our past, then the insurmountable step is implied to be in our future, and our prospects for reaching step 9, interstellar colonization, are slim. If the first stages were easy to implement, then many civilizations would have developed to the current level of humanity. However, no one seems to have reached the level that allows civilization to reach the 9th step, otherwise the Milky Way would be full of colonies. So perhaps step 9 is unlikely, and at the moment the only thing that could prevent us from reaching step 9 is some kind of cataclysm or resource depletion that will prevent us from taking the step due to lack of available resources or environmental catastrophe. The Search for Extraterrestrial Intelligent Project, or SETI, is one of the most fascinating and ambitious scientific endeavors of our time. Its goal is nothing less than to detect and communicate with intelligent alien civilizations in the universe. The SETI project has been ongoing for decades, and while it has yet to find any conclusive evidence of extraterrestrial life, it has made significant progress in our understanding of the universe and our place in it. The SETI project began in 1959, when scientists first started searching for radio signals from other planets. The idea behind this was simple. If there were other intelligent civilizations out there, they might be using radio waves to communicate with each other, just as we do on Earth. So scientists began scanning the skies for any unusual radio signals that might be coming from other planets. In the early days of SETI, scientists used large radio telescopes to listen for signals from space, but this method had limited success due to the vast distances involved and the interference from natural sources. However, in recent years, advances in technology have allowed scientists to search for signals in new ways. For example, the SETI Institute has developed the Allen Telescope Array, a network of small radio telescopes that can scan the skies more efficiently than traditional ones. Another major breakthrough in the SETI project has been the development of new algorithms and software that can analyze large amounts of data from radio telescopes. These tools allow scientists to search for patterns and anomalies in the signals they receive, which could indicate the presence of intelligent life. In addition to searching for signals from other civilizations, the SETI project also involves sending messages into space in the hopes of making contact with other worlds. One notable example is the Arecibo message, a radio message sent from Earth to a distant star cluster in 1974. While the chances of receiving a response to such messages are slim, they represent an important step forward in our efforts to communicate with other civilizations. The SETI project has received a number of signals that could potentially be messages from alien civilizations. One of the most famous examples is the WOW signal, which was detected in 1977 by a radio telescope in Ohio. The signal appeared to come from the direction of the constellation Sagittarius and lasted for 72 seconds, but it has never been detected again. One of the most recent signals that generated excitement among SETI scientists was detected in 2015 by a radio telescope in Russia. The signal appeared to come from a star system called HD 164595 and was a narrow-band signal, which is the type of signal that SETI scientists are looking for. However, the signal has not been detected again, and some scientists have suggested that it may have been caused by terrestrial interference. The search for extraterrestrial life inevitably leads us to the topic of the possibility of interstellar travel. Is it possible for an advanced civilization to travel such vast distances and reach other star systems? Or are all possible civilizations, including our own, forced to exist alone in the interstellar void until natural disasters, wars, or the death of their own star annihilate them? The idea of traveling beyond our solar system and exploring other planets and stars is an exciting prospect, but is it just a wild guess or is it a true possibility? Currently, the only way we can explore space is through robotic missions, which have been successful in providing us with valuable information about our solar system and beyond. However, sending humans on interstellar missions presents a whole new set of challenges. The biggest challenge is the vast distances involved. The closest star to us, Proxima Centauri, is more than 4 light-years away, which means it would take over 4 years to reach it traveling at the speed of light. The speed of light is currently the fastest known speed in the universe, and it would take an enormous amount of energy to propel a spacecraft to such speeds. Even if we could achieve such speeds, there are still other challenges to consider, such as radiation exposure, long-term life support, and the psychological effects of being isolated in space for extended periods. Despite these challenges, there are ongoing efforts to make interstellar travel a reality. One approach is to develop advanced propulsion systems that could take us beyond the limits of current technology. One such system is the Alcubierre drive, which proposes to warp space-time around the spacecraft, allowing it to travel faster than the speed of light without violating the laws of physics. We will discuss the concept of such a drive a little bit further. Another approach is to develop life support systems that could sustain human life for extended periods in space. This includes developing closed-loop systems that can recycle waste and generate food and water from available resources. In addition to technological advancements, there are also ongoing efforts to understand the psychological and social aspects of long-duration space travel. This includes studying the effects of isolation and confinement on crew members, as well as developing strategies to maintain mental health and well-being during extended missions. The Alcubierre warp drive is a theoretical concept that proposes a way to travel faster than the speed of light without violating the laws of physics. The idea was first proposed by Mexican physicist Miguel Alcubierre in 1994 and has since captured the imagination of many scientists and science fiction enthusiasts. The basic idea behind the warp drive is to create a bubble of space-time around a spacecraft that would allow it to move faster than the speed of light. This would be achieved by compressing space in front of the spacecraft and expanding space behind it, effectively creating a wave-like distortion in the fabric of space-time. The concept of the warp drive is based on the principles of general relativity, which describes how mass and energy can warp the fabric of space-time. According to the theory, a massive object such as a star or a planet can create a gravitational field that bends the path of light. The warp drive concept involves creating a similar curvature around the spacecraft, but on a much larger scale. To create the space-time bubble required for the warp drive, one would need to generate an enormous amount of energy. This energy could be provided by exotic matter, which has negative energy density and is not found in nature. The exotic matter would be used to create a region of space-time with negative energy density in front of the spacecraft and positive energy density behind it. While the idea of the warp drive is intriguing, there are many challenges to overcome in order to make it a reality. One major challenge is finding a way to generate the enormous amounts of energy required to create the space-time bubble. Another challenge is ensuring that the spacecraft remains stable during the travel, as any instability could lead to catastrophic consequences. Despite these challenges, scientists have conducted experiments to test the feasibility of such a drive. In 2012, physicist Harold White and his team at NASA's Johnson Space Center conducted a series of experiments using a modified Michelson interferometer to measure the effects of a small-scale warp field. The results were promising, but further research is needed to determine whether the concept can be scaled up to a practical level. Another concept for fast travel through space-time is wormholes. A wormhole is a hypothetical tunnel or shortcut through space-time that connects two distant points in the universe. The idea of a wormhole was first introduced by Albert Einstein and Nathan Rosen in 1935, but it wasn't until the 1960s that the concept gained wider recognition. Traversable wormholes are characterized by a tunnel or shortcut through space-time that can be traversed by spacecraft or other objects. The creation and maintenance of traversable wormholes would require immense amounts of energy and exotic matter to stabilize the wormhole and prevent it from collapsing. Any spacecraft passing through a traversable wormhole would be subject to extreme forces and radiation, making it a significant challenge for interstellar travel. The physics behind wormholes is also based on Einstein's theory of general relativity. Objects with mass cause a curvature in spacetime, and this curvature determines how objects move through space. In the case of a wormhole, the curvature is so extreme that it creates a tunnel through spacetime. To understand the concept of a wormhole, it is helpful to imagine a sheet of paper representing spacetime. If you were to fold the paper in half and poke a hole through it, you would create a shortcut between 2 points on the paper. This is similar to how a wormhole works, except that it involves a curvature of spacetime rather than a physical object. But there are many limitations and challenges associated with wormholes. One major limitation is the need for exotic matter to stabilize the wormhole and prevent it from collapsing. It is required to counteract the effects of gravity and keep the wormhole open. Some theories even suggest that there is a possibility that a wormhole could lead to a different universe or dimension, making it difficult to predict where the object that crossed it will appear. The Breakthrough Starshot project is a revolutionary initiative that aims to send a fleet of miniature spacecraft to Alpha Centauri, the nearest star system to our own, in just over 20 years. The Starshot concept involves launching a base spacecraft that will deliver around 1,000 tiny spacecraft into high orbit and then launch them one after another. Each microprobe is connected by super strong straps to a solar sail about 4 by 4 meters in size, 100 nanometers thick and weighing 1 gram. Then ground-based lasers focus a beam of 50 to 100 gigawatt power on the sail for 10 minutes. This will provide acceleration of about 30,000 g, allowing the probes to reach a target speed of 20% of the speed of light. The flight to Alpha Centauri will last about 20 years. If there are Earth-sized planets within the habitable zone, and so far only one of them, Proxima b, has been confirmed to exist, Breakthrough Starshot will attempt to target spacecraft within 1 astronomical unit of them. From this distance, the cameras will be able to capture an image of high enough quality to see the topography of the planet. To achieve this resolution with a space telescope in Earth orbit, this telescope would have to be on the order of 300 kilometers in diameter. The nanocraft will be equipped with a range of scientific instruments that will allow them to study the Alpha Centauri system in unprecedented detail. This includes imaging the planets and moons around Alpha Centauri, as well as studying the composition of system's asteroids and comets. One of the biggest challenges facing the Breakthrough Starshot project is ensuring that the nanocraft can survive the harsh conditions of interstellar space. To address this challenge, the team behind the project is developing advanced materials that can withstand extreme temperatures and radiation. They are also exploring innovative designs for the nanocraft that can help protect them from collisions with space debris. Another major challenge is ensuring that the nanocraft can communicate with Earth from such a great distance. To address this challenge, the team is developing advanced communication technologies that can transmit data from the nanocraft back to Earth in real time. This includes using lasers to send data across vast distances, as well as developing sophisticated algorithms that can handle the massive amounts of data generated by the nanocraft's scientific instruments. Despite the many challenges facing the Breakthrough Starshot project, it represents a major step in our understanding of interstellar travel and the potential for exploring the cosmos. If successful, it could open up new avenues for scientific discovery and pave the way for future missions to other star systems. The project is a testament to the power of human ingenuity and the endless possibilities of scientific exploration. The possibility of discovering new worlds and encountering extraterrestrial civilizations has inspired countless works of science fiction, but it is also a field of serious scientific inquiry. While interstellar travel may still be a wild guess at this point, the rapid pace of technological development suggests that it may not be too far off in the future. Through constant research and development, the dream of interstellar travel and finding alien intelligence may one day become a reality.